Hi, physics, Mr. Janowski. This is part 6 of the chapter 36 slides. So this chapter is about magnetism, and that's mostly what we've been talking about, except in the last part we were talking about torque, which is really a physics 1 concept that we never got time to do. So now we're going to take that idea of torque and all the things we've been learning about magnets, put them together, and see how an electric motor works. So some of these slides have drawings that I made in Google Drawings, and they were such a nightmare to make. So you better appreciate this one. So let's get started. So first, to review, what is a long wire with many turns called? This is called a solenoid. And there's your formula for the magnetic field in a solenoid. So what do you get when you put an iron core inside of such a device? Inside of a solenoid, you get an electromagnet. Now, what is the formula for the force on a current-carrying wire in a magnetic field? That formula is, the one we're going to use is F equals ILB sine theta, where I is the current, L is the length of the wire, B is the strength of the magnetic field, and theta is the angle between the direction of the wire, so the direction of the length, really, and the magnetic field. What three things does torque depend on? So this is the thing we learned in the last part of the slides. Torque is going to depend on the magnitude of the lever arm, which is the distance from the pivot to where you're applying the force. It will also depend on the magnitude of the force. So bigger magnitude gets you more torque, and also the sign of the angle theta between them. So think about the behavior of the function sine theta. So when theta is 0, sine of 0 is 0. And when is sine of theta maximized? It's when theta is 90 degrees. So when you have a right angle, that's the angle that's going to get you the most torque. And then just like left and down, let me say it the other way. Just like right and up are positive, when we're dealing with rotational motion, we consider counterclockwise to be the positive direction. And just like left and down are negative, we consider clockwise to be the negative direction. I think I said both parts of that right. I don't know. We'll see. So how does a motor work? So this is one of those drawings that took me forever. There's a bunch of drawings like this. So consider this loop of wire we have carrying this current of I into this magnetic field. So the current is coming up here along this left part of the wire, making this left turn, getting to this corner A, going to B, going to C, up to A, to B, to C, down to D, and then back out through the wire. So use the right-hand rule, the cross product right-hand rule, to figure out what is the direction of the force in segment AB, and then in BC, and then in CD, and then in DA. So for the last part, consider D back to A. Notice how the current's all going in the same direction here, even though it's not actually connected right here. So just consider D to A like one big long thing. So quickly apply the right-hand rule and figure out the direction of the forces. The direction of the forces will be as such. So if we're looking at A to B, so the current is going into the page, so point your thumb away from you. The magnetic field is going left to right, so point the fingers of your right hand to the right. And which way is your palm facing? Your palm is facing down. So A to B, the force is going down. And then from B to C, okay, which way is the force going? Well, the current is going to the right, and the magnetic field is also going to the right. So if you point your hand that way with your thumb against your index finger, that isn't how the right-hand rule works. Because the angle between the direction of the current, which is your thumb, and the magnetic field is 0, and sine of 0 is 0, so we don't get any force there. How about C to D? So this is the part of the current that's coming back towards us out of the page. So if you point your thumb towards you and you point the fingers of your right hand to the right, your palm will be facing upwards. So that one's going to push up. And D to A, just like B to C, because of the right-hand rule, you don't have any force along this segment. So A to B, you've got a force going down. B to C, you have nothing. C to D, you have a force going up. And then D to A, you have nothing. So next question. What kind of torques will these forces cause around the axis turning into the page, or the axis running into the page? So this dashed line, this dotted line, going into the page. So imagine we've got this thing set up so that it can spin along this axis. So what kind of torques are these going to cause? So don't think positive and negative, think clockwise or counterclockwise. So the force from section A to B, what kind of torque is that going to cause? That's going to cause, well, here they all are. A to B is going to cause a counterclockwise torque. Hopefully you can see that it's going to make this thing want to rotate that way. B to C, there's no force, there's no torque. C to D, you've got a force going up, so that's also going to be counterclockwise. And then D to A, you have no torque. So look at this picture, and I mean, this didn't take as much time to do, and maybe it shows the idea more clearly. So if you're looking at the section A to B, remember that section's going into the page right there. And then, so that's why we have the little feathers here. So do the right-hand roll on that part, and you'll see it's going down. And then B to C is kind of here. You can't really see that one very well. C to D is coming towards you, so do the right-hand roll again. You'll see that force is going up. And then D back to A, again, you can't really see that one. So yeah, when you're going through these slides, kind of compare this three-dimensional-ish, I guess this is called 2.5D picture to this one, this 2D picture representing the same idea. But yeah, hopefully you can see that both of these forces are going to make this thing try to spin around. This little dot in the middle here, this is the pivot. So both of them are going to make this thing turn counterclockwise. So we have counterclockwise torque. So this loop is going to start to spin counterclockwise. So we've just done something important here. We are turning electrical energy into mechanical energy. We have started to create a motor. However, as we'll see as this thing develops, we haven't completely built the motor yet. So we've started to get something to turn. That's what a motor does. But we're going to run into a problem. So follow along. So at this point, look at your formula for torque and notice that we are going to have a lot of torque. This is as much torque as we're going to get out of this. Because, yeah, we've got this big R and we've got this big F, and the angle between them is 90 degrees, and sine of 90 is equal to 1, and that's as big as sine of theta is going to get. So this is when we have the most torque. So our force is at right angles to our lever arm. So we're getting a lot of counterclockwise torque from force AB, and we're getting a lot of counterclockwise torque from force CD. So what's going to happen as this thing starts to turn and it goes counterclockwise 45 degrees? So you'll see the forces stay the same and the R's stay the same. The thing that changes is the angle between them. And the angle between them is 45 degrees. I know it looks like it's 135, but you wouldn't actually measure the angle from here to here. You would have to take the tail of this one, match it to the tail of this one, and then the angle you'd have in there, that would be 45. That's how you actually measure the angle. So anyhow, yeah, our forces are still going in the same direction and they're acting on the same points, but the angle has changed, and sine of 45 degrees is less than 1. It's less than the sine of 90 degrees. So we're going to get less torque out of this situation. So we started with a lot of torque on this slide in this situation, and now we still have counterclockwise torque, but we have less of it. So think now, what's going to happen once this loop is turned all the way to 90 degrees? Well, R's are still the same, and the F's are still the same, and they're still going in the same direction. However, now the angle between our lever arm and our force is actually 0 degrees, and sine of 0 is 0. So we're not getting any torque. So we're not getting any force to keep this thing turning. Now this thing will keep turning because it has angular momentum. It's already spinning, so the fact that we're not giving any torque on it now, it's going to keep spinning because it was spinning. It's going to keep that motion, but we're not adding any more torque. We're not causing it to spin anymore. Now think this is where we really start to run into trouble, is what's going to happen once this loop turns a little bit further? What happens once this loop turns past 90 degrees? Well, we've still got the current going the same way. We still have the same R's and we still have the same F's. But now that this thing has rotated past 90 degrees, now we're going to end up generating clockwise torque. So let me jump back 2 slides, 3 slides. So notice these torques down here in this picture. These torques make this thing want to go counterclockwise. And then it turns a little bit, and it still goes counterclockwise. It still wants to go counterclockwise. And then we go a little bit further. So now we have no torque, but because the thing was already spinning, it's going to keep spinning for a while. So it'll coast right past this point. Still going counterclockwise. But once we get to here, now the torque that's being generated is clockwise. So this is going to actually kind of cancel the thing out. So we started spinning one way, and now it gets to this point, and it's going to want to go back the other way. So this is not a very good motor if it can only turn, halfway around and then stop and then come back the other halfway around. This is not a super useful thing we've got here. So in order to keep our motor running and to keep it turning in the direction we want, which in this case is counterclockwise, we need to have a way to switch the direction of the current going through the loop. Because if you look at this picture, notice if all of a sudden we can switch this current here to being into the page and this current here to being out of the page, then the forces are going to flip, and we'll have forces again that keep this thing, we'll have torques again that keep this thing going counterclockwise. So yeah, we need something that's going to flip the direction of the currents for us. So the thing that does that is called the commutator. So yeah, these are some of the drawings that took a really long time. And I got this weird little, this is not even in the drawings, this weird little cutout here, this little dash, like goofy things were happening. But yeah, whatever, I don't know, it's weird. So yeah, I've added this part here. This is the commutator. Well, technically this part right here is the commutator. And these are the brushes. But yeah, this drawing here, let me go back. This would be hanging off on the end right here. So I didn't add it to this drawing. There's too much detail going on, so I just made separate drawings for this. So yeah, now we've got our loop back to where it started. And this is the commutator. So the way this works, what the commutator is it's this ring going around, and the ring is connected to the loop. So this part of the ring, maybe I could have labeled them. This part is connected to, we'll call this the A part. And then the current goes around here and comes back through here. And this part is connected to the D part. And the commutator is made out of a conductive material, so it's made out of metal. And then we have these things called brushes. These are typically made of carbon, and carbon is a conductor. And we've got this connected to the positive terminal of some kind of voltage source. So what's going to happen here is current's going to come up through here, go through the brush, hit this part of this split ring, travel through the loop going this way, go up, and the top of the loop is not pictured, but it would go up along here, come back down, get to this part of the split ring, go back through the brush and come through here. So yeah, that's how the commutator works. So more drawings that took me a long time. So yeah, let's go back to this position. So this was kind of the one we started at. So yeah, our forces are at right angles to our lever arms. So we've got a lot of torque. And now this thing's going to start to turn. So it's turned 45 degrees. Now notice the split ring and the commutator is still keeping current going this way through the loop. Going back through here, and everything's good. And then we get to this one. Now, it's a split ring. And so at these little gaps, the brushes stop touching the ring. So at this point, what actually happens is we have no current. So not only do we have no torque, we actually have no force because there's now no current going through this loop. So the loop keeps turning, and this is where the magical thing happens. Now we get to this part, and notice the direction of our current through the loop is actually flipped. So in the first one, we started A on the left, going around, coming down through D on the right. Skip ahead, and now A is on the right. So now the current is going through the D part and up from D to C, from D to C to B back to A. Now the current's going the opposite way through the loop. And what this does, now look down at this picture, by keeping the current going, by making the current go the opposite way through the loop, we now have forces that continue to cause counterclockwise torque. So here are the stages I drew. So 0 degrees, look at how the current's going, look at the forces, look at the torques. 45 degrees, 90 degrees. So at this point, the brushes are lined up with the gap. So we've got no current going and no kind of torque. And then as this thing keeps going, now we've got positive current going into the D part and then back all the way around and coming through the A part this way. So the commutator is the thing that actually flips the current for us. So in this little GIF here, if we're looking at this, the red is the direction of the current. And the blue in this graph is going to be the amount of force we're getting, not the amount of torque. The amount of torque is going to vary sinusoidally, but this is the amount of force that's being generated. And notice at the point where you get to the little gap, you have no current and you have no force. So this is one way to build a motor. There are many different designs. This is a brushed motor is what this is called because it has little brushes. There are ways to make brushless motors that are better for lots of applications. But yeah, this is the simple kind of motor. All motors are going to basically work on this principle in some way. You're going to have magnetic fields interacting to cause this thing to turn. And then periodically, you need to flip one of the magnetic fields, which you do by flipping the current. So if we're watching a motor, important parts of the motor, well, we already learned how, what the commutator is. This is the thing that reverses the direction of the current. Motors are going to have some kind of magnet or electromagnet, typically an electromagnet, that rotates. That's called the rotor. And you're going to have a part that stays put. It is stationary. It is in stasis. And that part is called the stator. So here in the drawings I made and in this one, the stators look like they're just permanent magnets. These in all likelihood would be electromagnets as well. So in the one I drew, this is kind of the simplest type of motor you can make almost. There's only 2 splits in this. So it's just going to always go one way and then it's always going to go the other way. In the GIF up here, you can see there seems to be more splits. First of all, mine has like 2 lobes in this loop. This one seems to have 3, and it seems to have 6. You can do it that way. And in this is a picture of an actual commutator. Notice that there are many more splits. So it turns out the more splits you have, the more even the torque you're going to generate is. Because notice, let me go back to this picture. So we had maximum torque at 0, and then less torque at 45. And then when we finally got to 0, we would have had very little torque. The advantage of having many more splits than we had is as soon as the torque starts to drop because you start getting away from 90 degrees, it's going to flip to the next one. So I don't know how many we have here. It might be 12. Let me say it's 12 because 12 in the 360 is 15, I think. Should be able to do that in my head. Nope. 360 divided by 12 is 30. Okay. Yeah, I really should have been able to do that in my head. Anyhow, so say instead of having 2 of these things, so you go from 90 degrees almost down to 0 degrees where you have basically no torque. If you have 12 different, kind of splits in this thing and 12 different pieces, your torque is going to go from, your theta is going to go from 90 degrees and it's going to go down to about 60 and it starts to drop, but then right away it switches to the next one and it's back up to 90. And then it goes down to 60 and it drops, it drops as it goes down to 60, but then it goes to the next one. So this is the advantage of having more than one, more than 2 pieces to your commutator. So I'll put a link to this video. This is a nice little video from Mr. Wizard. So Don Herbert was Mr. Wizard, great science educator from way back in the day. He had TV shows like in the 50s and 60s and 70s. And then on Nickelodeon in the 90s, he had a TV show. And I honestly, growing up, I watched a lot more of Mr. Wizard than I ever did of Bill Nye. So yeah, Don Herbert, great early science educator, and a hero of Bill Nye. So Bill Nye's quote, if any of you reading now have been surprised and happy to learn a few things about science watching Bill Nye the Science Guy, keep in mind, it all started with Don Herbert. So yeah, Bill Nye is kind of a later version of Don Herbert, and Bill Nye would have watched Don Herbert, Mr. Wizard, growing up. So in this short little video, it's Mr. Wizard showing a young student how how electric motors work. Yeah, and it's a good video. Mr. Wizard, nice guy. So to review, what is your formula for torque? Magnitude of torque is equal to magnitude of the lever arm times magnitude of the force times sine of theta, where theta is the angle between the lever arm and the force. So yeah, torque is going to be maximized when theta is 90 degrees, and it's going to be minimized when theta is 0 degrees. So what is the part of a motor that switches the direction of the current? That is the commutator. So commutator, think like a commuter. A commuter is someone that moves. So that's what a commutator is. It moves, it flips the current and therefore the magnetic fields. So in an electric motor, you have magnets that turn. What do we call the magnets that turn? Those are the rotors, or rotor, the whole thing, I guess what you would call the rotor. And you also have magnets that don't turn. And what are those called? Those are called the stator. So again, there are lots of different designs for electric motors. This is a fairly simple design, and it's really the right one to learn how electric motors work. But they all will, in general, work on this principle. You're going to have magnetic fields interacting, and as the thing turns, you periodically need to flip one of the magnetic fields by flipping the direction of the current. So they all work on that principle. They don't all work exactly in this way. But yeah, that's how an electric motor works. And obviously, electric motors are hugely important. Yeah, you use them all the time. So that's it for this part. Hopefully you will all major in electrical engineering after having watched this, because I spent a hell of a lot of time making those drawings. Google Drawings is not a great program, and I'm not a great digital artist either. So hope you liked it.